In this video, we introduce ourselves to chemical bonding and look at the three main types of bonding we see in elements and compounds. When atoms or ions are strongly attracted to each other, we say that a chemical bond exists between them. Chemical bonds are strongly attractive forces that hold atoms together in complex units, such as in molecules or in ionic compounds. Chemical bonds involve the interaction of valence electrons from the combining atoms. The electron configuration and the distribution of electrons around the nucleus therefore play an important role in chemical bonding. Chemical bonds may result from the electrostatic attraction between particles of opposite charges, such as the metallic bonds that hold together metals or the ionic bonds that hold together ionic compounds, or they may be the result of sharing of electrons, as in the covalent bonds that hold molecules together. In all cases, it is the interaction of valence electrons that defines the nature of the chemical bond. Broadly speaking, there are three types of chemical bonds that exist in chemical substances: metallic bonds, ionic bonds, and covalent bonds. Metallic bonds are formed between atoms in metallic elements such as copper or gold or any other metal from the periodic table. Ionic bonds exist between positively charged cations, usually metallic in nature, and negatively charged anions, usually non-metallic in nature. The classic example being sodium chloride or table salt. Covalent bonds are formed between non-metallic elements in molecular compounds and molecular elements. In the reaction between elemental sodium and elemental chlorine to form sodium chloride, all three types of bonding are evident. Metallic bonds hold the atoms together in elemental sodium. Covalent bonds hold the atoms of chlorine together in the Cl2 molecule. And sodium ions and chloride ions that are formed during this reaction are held together by the electrostatic ionic bond. Let's have a closer look at all three types of bonding, starting with metallic bonding. Metallic bonding can be described in terms of the electron sea model, which describes the attraction between atoms in metals. In this model, the metal is pictured as a regular arrangement of metal cations in a sea of mobile valence electrons, as depicted in this diagram. The metal cations are actually comprised of the nucleus of the atom plus all its inner or core electrons. The sea of electrons is comprised of mobile valence or outer shell electrons. The negatively charged valence electrons are confined to the metal by the electrostatic attraction to the positively charged nuclei, and they are uniformly distributed throughout the three-dimensional structure of the metal. The valence electrons are considered to be mobile, and no individual electron is confined to a particular metal nucleus or metal ion. In the presence of an electric field, such as when a metal wire is connected to the terminals of a battery, the valence electrons become highly mobile and they jump from nucleus to nucleus and show a net flow of valence electrons through the metal towards the positive terminal of the battery. This model is adequate to explain a range of metallic properties, including the ease of formation of cations, as well as the physical properties of electrical conductivity, thermal conductivity, ductility, and malleability, although the model is somewhat limited when it comes to explaining trends in melting points of metals. An ionic bond is the attractive force that exists between ions of opposite charge, and specifically describes the bonding that occurs in ionic compounds. One way that ionic compounds can be formed is through the chemical reaction of its constituent elements. For example, consider the formation of sodium fluoride from elemental sodium and elemental fluorine. The neutral sodium atom contains a total of 11 electrons, 2 in the 1s subshell, 8 in the n equals 2 shell, spread across the 2s subshell and the 2p subshell. These 10 electrons constitute the inner or core electrons of the sodium atom. The 11th electron, the sole valence electron, resides in the 3s subshell. This gives an overall electron configuration of 1s2, 2s2, 2p6, 3s1. The neutral fluorine atom has 9 electrons in total, 2 in the 1s subshell, and 7 in the n equals 2 shell spread across the 2s subshell and the 2p subshell. This gives an overall electron configuration of 1s2, 2s2, 2p5. When the two atoms come into close proximity with each other, under the right conditions, the 3s electron from the sodium can be transferred to the outer shell of the fluorine atom, giving both atoms a full complement of electrons in their outermost shell, which we know is a stable electron arrangement for both. Of course, during this electron transfer process, a positively charged sodium cation is formed and a negatively charged fluorine anion is formed. The electrostatic attraction between these ions of opposite charge constitutes the ionic bond, which holds these atoms together in a semi-infinite three-dimensional crystal lattice structure. We can represent this electron transfer process in a different way using a chemical equation that includes the electron configurations of each atom. For example, we can see that the 3s valence electron from sodium is transferred to the outermost shell of fluorine, resulting in a sodium ion with a stable neon core of electrons, and a fluoride ion that has a helium core plus 2s2, 2p6, which also happens to be the electron configuration of neon, which again we know is stable. It is also important to note that the formation of ionic compounds can also occur from already existing ions where the electron transfer process has already taken place. In fact, this is by far the most common way that ionic compounds are formed. An example would be the formation of the solid precipitate silver chloride, AgCl, from a solution of silver nitrate and a solution of sodium chloride. In precipitation reactions such as these, the formation of ionic compounds depends on the solubility of certain ions in the presence of other ions. And in order to predict the formation of ionic compounds in this way, we need to refer to our solubility rules. A covalent bond results from the sharing of one or more pairs of electrons between atoms. The electrons that are shared between two atoms are valence electrons, which are attracted to the positive nuclei of both atoms in the bond. A covalent bond is therefore defined as the attractive force that results from two nuclei attracting the same shared electrons. In the covalent bond model, atoms share valence electrons in order to achieve a favorable electron configuration. For example, we see that a hydrogen atom has a single 1s electron in its electron cloud, which we know is not a stable arrangement. By sharing an electron with another hydrogen atom in forming the H2 molecule, each atom can now be said to have two electrons surrounding its nucleus, and this is a much more stable electron configuration. As an example, think of the electron cloud of helium, which has two electrons around its nucleus. The covalent bond model involving electron sharing is used to describe the attraction between atoms in molecular substances, that is, molecular compounds or molecular elements. As another example, we could consider the formation of the F2 molecule from single fluorine atoms. A single fluorine atom has 9 electrons in total, with 2 inner or core electrons plus 7 valence electrons in its outermost shell. The electron configuration of fluorine with the helium core, 2s2, 2p5, is not stable. By bringing two fluorine atoms together and sharing one electron from the valence shell of each atom, the F2 molecule now has 8 electrons surrounding each atom in the outermost valence shell, with a total of 10 electrons each overall. And this is similar to the electron cloud of neon, which we already know is a noble gas and therefore represents a stable electron cloud. A third example, this time involving the binary molecular compound water, H2O, involves a central oxygen atom bonded to 2 peripheral hydrogen atoms. The oxygen atom has 8 electrons in total, with 6 valence electrons in the outermost n=2 shell and an electron configuration of 1s2, 2s2, 2p4. The 2 individual hydrogen atoms have a single electron each, with both having an electron configuration of 1s1. Neither the oxygen nor the hydrogen electron configurations represent stable electron clouds. However, sharing of one electron from each hydrogen atom with the outermost shell of the oxygen atom results in all 3 atoms achieving a stable configuration, with both hydrogen atoms now having 2 electrons in their electron clouds, which we know is stable, and the oxygen atom having 8 electrons in its outermost valence shell, which we also know is stable. In upcoming videos, we will see how this propensity for the formation of 8 electrons in the valence shell of many atoms within bonds is generalized via the octet rule. And we will also see how the use of Lewis symbols and the creation of Lewis structures allows us to easily track the valence electrons of atoms during bond formation.